Here's the second part to topic 8, recap of the last slide. This section going to begin with looking at renewable resources versus non-renewable resources that we talked about in the last section. Renewable resources are cleaner than fossil fuels, but there is a disadvantage. The disadvantage is that they have a high startup cost. Also, living plants convert sunlight plus CO2, carbon dioxide, into plant matter. That's a good thing because all of that can be used as a fuel, and since it's renewable, plants die, right? Then it can be a resource that we can use. For instance, Australia uses a lot of renewable energy, such as wood, hydroelectric, solar, wind, biomass, etc., etc. So other countries are definitely jumping on board with the renewable resources. Let's talk about wood and biomass. Energy that comes from the sun is going to be able to fuel wood and biomass fuels. It is the oldest form of heating. More particularly, wood is the oldest form of heating. Some examples include sugarcane, fats, food waste, and manure. Brazil, for instance, uses a lot of biomass and wood as their heating, as their energy resource, as the pie chart to the right denotes here. One disadvantage, though, is that it must be burnt in order to produce energy. Therefore, it contributes to the greenhouse effect. But biofuels produce little energy because the plants can take in the CO2. Therefore, you would see a reduction in the greenhouse gases. So although biofuels, such as wood and biomasses, do produce some CO2, the plant life that is in the area can take in the CO2, thus reducing the emissions of greenhouse gases due to the use of biofuels. Okay, nuclear fuel, energy that does not come from the sun, energy that does not come from the sun, such as fission. The idea of fission is the splitting of unstable nuclei to produce energy. It is an example of a non-renewable resource, but it's no contribution to the greenhouse effect. But you still get waste. These wastes that you get are radioactive waste, which are hard to dispose of, so that is a disadvantage that you would see. Your first picture here on the left shows you an example of the process of fission. Over here showing you a pellet of uranium oxide is what that means, but it's, uranium. They insert that into a fuel rod. Those fuel rods are all inserted into nuclear reactors, into a nuclear power plant. Fusion fuel. So instead of fission, now we're going to talk about fusion, where atoms are fused together. Hydrogen, that's your big player here. Hydrogen is used as the fuel to produce energy in fusion. Okay, hydrogen is the fuel for fusion. It is a non-renewable resource, but there's a ton of water on Earth because fusion requires water to run. It produces a lot of energy from a little bit of hydrogen. Okay, a lot of energy from a little bit of hydrogen. Take an example here, some deuterium. Look at how small a piece of deuterium is. You get that much kilojoules, that much energy per gram. That's huge. Think about a Twinkie. A Twinkie gives you 15 kilojoules per gram. And then look at a piece of deuterium or tritium, which is H2 and H3 respectively. So, nuclear energy, scary, but very, very good. Okay, energy density. Energy density is measured in megajoules per kilogram. And the highest players here for energy density, the most dense are going to be fusion and fission, and then the lowest are going to be coal and oil. So here this chart shows you an example of some different density energies. Other sources is solar energy. Solar energy is used to heat something, and then by heating something, it is going to make electricity. It's used to focus energy from the sun. How does it do this? It uses mirrors. It uses mirrors or photovoltaic cells. Photovoltaic cells are abbreviated PV cells. Okay, so you're either going to focus that energy, that solar radiation, i.e. sunlight, by use of mirrors or PV cells. Specifically, PV cells are used to turn sun's energy directly into electricity. Okay, that's pretty cool there. The PV cells, not really going to take a lot then, right? The PV cells are used to turn the sun's energy and directly into electricity. These would be PV cells. Obviously, these are mirrors. This is the rice power plant that is potentially used to power the strip in Las Vegas. You can imagine how much electricity it takes to power Las Vegas up. Look at all those mirrors though. They also have this in Spain. Spain has another solar power plant that they use. I believe it is Madrid, but it might be Barcelona, although I'm pretty sure it's Madrid that they use to power the energy for electricity for that city. Solar energy is more efficient when? Well, in the summertime, of course, because there's more direct sunlight. That sunlight can get through the clouds a lot easier because usually there is less cloud cover during the summertime. But what we need to discuss is something called the solar constant. This is intensity. Remember, intensity, power over 4 pi r squared, watts per meter squared. Okay, so intensity of the electromagnetic spectrum, or different portions of the radiation from the EM, electromagnetic spectrum, emitted from the sun per Earth's orbital radius. It's equivalent to roughly 1380 watts per meter squared. So that's how intense our solar constant is. The amount of solar energy that we get depends on the amount of sunlight that we get. So there should be a direct relationship seen there. The increase in amount of sunlight, increase in amount of solar power. So clearly if you're going to heat your house with solar power, you need to live in a very sunny area. Solar heating panels are used for solar heating and for generating hot water for household use. Where are they usually placed then? On rooftops. China has a ton of these. This is a really big use of heating in China. How does this work? Solar radiation enters through the glass cover. It's absorbed by a black metal plate that heats up, which then heats this water through conduction. Water continuously is circulated. So in other words, the hot water flows out, the cold water flows in. Hot water flows out, cold water flows in. So as soon as that cold water is turned into hot water, more cold water may be used. Cyclic process. Back to photovoltaic cells. They convert solar radiation into electrical energy by use of semiconductors. What these semiconductors do is they release an electron when photons of light are absorbed. How does this differ than that of a battery? Well, these solar voltaic cells use light energy to get the electricity, generate electricity, I guess I should say. Also, furthermore, it is a battery that starts off with chemical energy. So the photovoltaic cells, the solar panels, are going to use light energy from the sun, solar rays. The potential difference, the voltage that you get here, from one cell, it's very little. So that's why usually the entire rooftop should be covered in photovoltaic cells in order to produce a nice amount of energy. Moving on to hydroelectric power. Hydroelectric power, the sun heats up the water, which then turns into water vapor that rises. It forms clouds. Those clouds then condense with squeeze together to give rain. Rainwater has a high amount of potential energy. So, as this potential energy, i.e. water, is running down a hill, it can be made to do work. Because then it's obviously moving, it's converted into kinetic energy, the ability to do work there, therefore that work can then be used to produce electricity. So here's a really good slide showing you the inside mechanics, the workings, of a hydropower plant. Obviously, there needs to be a high area that flows downhill in order for you to generate that electricity. Here is the world's largest hydroelectric power plant, which is found in China. Check that out. That's very large. Think about the Hoover Dam, like the size of the Hoover Dam over Mead Lake. That's definitely got to be. Okay. Where does the energy originally come from? Well, the sun, of course, because that's what's going to heat up the water to make it rise. The energy stored that's in a lake, the amount of energy stored in a lake can be calculated by determining the gravitational potential energy, your PE, right? Because if we go back here, it says that the water has a high amount of potential energy. So the potential of amount of electricity that can be generated from this lake can be determined by, is really what we're talking about here. You want to see what this height difference is. Remember back on this slide here, we want to see what the height difference is going to be here. Okay, so you want to try to calculate H first, in which you're going to use GPH. That came out wrong. You're going to use MGH to figure out what the GPE is. from the outlet of the lake to the turbine. The turbine's doing the turning. This is an example of the water cycle. So this kind of is the beginnings of how a hydroelectric power plant would even be able to work. Obviously, there has to be fall of water to fill up the lakes. Now from this then, we're going to look at some calculations that we saw previously. And with that in mind, first thing we want to look at is that the average height, now this is just in general, okay? The average height is going to be 87.5 meters. I don't expect you to know that from this problem, okay? I'm just telling you that. Well, I guess you could say 100 meters above, and the turbine's at 75 meters, so 175 divided by 2 is the 87.5. Okay, so anyways, volume of lake. Is going to be 2,000 times 1,000 times 75, which gives you 5 times 10 to the 7th meters cubed. The mass of the lake is going to equal volume times density, in which the volume is 5 times 10 to the 7th, and the density of this lake is 1,000. So that makes that 5 times 10 to the 10 kilograms for your mass of your lake. Now we can use our GPE, and our GPE is MGH, in which our M is 5 times 10 to the 10th, your G is 9.81, and your H is 87.5, sorry. Your H is 87.5. So multiplying then, you get like 4.91 times 10 to the 13th. And if you only want to take one sig fig from the 5 times 10 to the 10th, that gives us 5 times 10 to the 13th joules. That's the energy. That is the total energy stored. That's what your GPE equals. So then the power, if water flows at a rate of 1 cubic meter per second, then 1,000 kilograms, the mass of this lake, would fall at 87.5 meters per second. So therefore, energy lost by water equals 1,000 times 9.81 times 87.5. That's MGH there, right? You're just using MGH, which gives you 875,000 joules per second. Well, 875,000 joules per second therefore means that the power is 875 kilowatts. A joule per second is a kilowatt. So your power is 875 kilowatts. Okay. Run of the river is a hydroelectric power scheme, and diversion is another hydroelectric power scheme. Run of the river scheme uses water that has been diverted from a fast-flowing river without damming it up, whereas diversion is building a small-scale power station near where people live. You build plants dependent on the electricity near hydroelectric power stations, which reduces energy loss due to heat generated when electricity passes through the wires. Pretty cool there, right? But obviously these are going to be probably rather expensive to build just for each individual city. Next thing we can look at is tidal power, in which tidal flow can be used to drive turbines and produce hydroelectric power. Where would you place a turbine? Well, you're either going to fix it to the bottom of an estuary or build a dam across an estuary, and that's where you're going to place your turbine that obviously has a generator in it that turns for the power to make the electricity become generated. All right, we're going to stop here and then pick up with wind power.